amount of pressure drop across an orifice depends on both the flow rate and the size of the orifice. If flow remains constant, the smaller the orifice, the greater the pressure differential. If flow rate drops, the pressure differential also drops. If flow is blocked downstream, pressure becomes equalized on both sides of the orifice. However, if flow remains constant, the differential remains constant, causing upstream pressure to rise if downstream pressure rises. Many of the valves in complex hydraulic systems take advantage of these principles.
Series and parallel circuits. Most machines require multiple components that can be connected in series or parallel. Figure 25. When components are connected in series. 1. Fluids flow from one component to the next before returning to the tank. When components are connected in parallel, 2. Fluid flows through each component simultaneously. Restrictions in series. In Figure 26, a pressure of 620 kilopascals, 90 psi, is required to send 4 liters per minute, LPM, through either circuit. Orifices or relief valves in series in a hydraulic circuit offer a resistance that is similar to resistors in series in an electrical circuit, in that the oil must flow through each resistance. The total resistance equals the sum of each individual resistance. Restriction in parallel. In a system with parallel circuits, pump oil follows the path of least resistance. In Figure 27, the pump supplies oil to 3 parallel circuits. Circuit 3 has the highest resistance and therefore would have the lowest priority. Circuit 1 has the lowest resistance and therefore would have the highest priority. When the pump oil flow fills the passage from the pump to the valves, pump oil pressure increases to 207 kilopascals, 30 psi. The pressure created by the restriction of oil flow opens the valve to circuit 1 and oil flows into the circuit. Circuit pressure will not increase until circuit 1 is full. When circuit 1 fills, fluid pressure will increase to 414 kilopascals, 60 psi, and opens the valve in circuit 2. Again, circuit pressure will not increase until circuit 2 is full. Pump oil pressure must exceed 620 kilopascals, 90 psi, to open the valve in circuit 3. There must be a system relief valve in one of the circuits or at the pump to limit the maximum pressure in the system. Hydraulics doing work. In order to perform useful work, a hydraulic system must convert and control energy as it flows from one component to the next. Figure 28 above represents the key conversion and control points in the system. The hydraulic system receives input energy from a source, normally from an engine or rotating gear train. The hydraulic pump converts the energy into hydraulic energy in the form of flow and pressure. Valves control the transfer of hydraulic energy through the system by controlling fluid flow and direction. The actuator, which can be either a cylinder or a hydraulic motor, converts hydraulic energy into mechanical energy in the form of linear or rotary motion, which is used to perform work. To perform hydraulic work, both flow and pressure are required. Hydraulic pressure is force and flow provides movement. Imperial metric conversion factors. Length 0.03937 inches. Ins equals 1 millimeter. Mm 0.3937 inches. Ins equals 1 centimeter. Cm 39.37 inches. Ins equals 1 metro. M 1 inch. In ore equals 25.4 millimeters. Mm 1 foot. FD ore equals 0.3048 meters. Area 0.00155 ins 2 equals 1 square millimeter. 0.155 ins 2 equals 1 square centimeter. 1 square inch in 2 equals 6.452 square centimeters. cm2 volume 0.061 in 3 equals 1 cc. 61.02 in 3 equals 1 liter. L 0.22 imperial gallon equals 1 liter. L 0.2642 U. S gallon equals 1 liter. L 1 cubic inch in 3 equals 16.39 cubic centimeters. cm3 or cc1 imperial gallon gal equals 4.546 liters. Lieutenant 1 US gallon gal equals 3.785 liters. Lieutenant. Mass 2.205 pounds. Pound equals 1 kilogram. Kilogram 0.9844 tons. T equals 1 ton. T 1 pound. Pound equals 0.4536 kilograms. Kilogram, the velocity, 196.8 feet per minute. Foot per minute equals 1 meter per second. Meter per second. Force, 0.2248 pounds force. Pound, force, equals 1 Newton. N, 0.104 tons force. T, force, equals 1 kilonewton. Knots, pressure, 0.145 pounds per square inch. Psi equals 1 kilopascal. kPa, note, 101.325 kilopascals equals 1 atmosphere. ATMS, 1 kilogram per square. cm equals 14.22 psi or 0.9678 ATMS or 100 kilopascals. Torque, 0.7376 pound-foot. Pound. FD equals 1 Newton meter. Nanometer, 7.23. Pound. FD equals 1 kilogram per meter. Temperature, degrees Fahrenheit. Degree F equals degree C by 1.8 plus 32. Degrees Celsius degree C. Per 1 kilowatt kW equals 1.341 horsepower HP. Note 1 watt W equals 1 Newton meter per second. Prefix is commonly linked to base units. Micro equals 0.0001 million. Milli equals 0.01 1000. Centi equals 0.01 100th. Deci equals 0.01 1/10. 1.0 equals 1. Deca equals 10.010. Hecto equals 100.0 100. Kilo equals 1000.0 1000. Mega equals 1 million.0 1 million. Hydraulic circuit and components. Figure 29 depicts a basic hydraulic system. For a basic hydraulic system to operate, e.g., cylinder extend and retract, it must contain the following components. Fluid. A. Reservoir. B. Filter. C. Pump. D. Directional control valve. E. Actuator or hydraulic cylinder. F. Lines. G. Pressure control valve. H. Cooler. I. Most manufacturers use graphic symbol circuits to identify the circuit components and to illustrate the circuit function and operation. Mobile earth-moving machines are designed with hydraulic systems which use a variety of hydraulic components to provide efficient operation. Hydraulic cylinders of various types are used to operate implements e.g. buckets, blades, rippers, backhoes, and truck beds. Hydraulic motors drive tracks, wheels, car bodies, and conveyors. Brakes, steering, transmissions, suspensions, and other vehicle systems rely on hydraulics for power and control. Graphic symbols. Graphic symbols for fluid power diagrams. Figure 30 were originally developed by the American National Standards Institute, ANSI, and are presently adopted by the International Standards Organization, ISO. They provide communication standards that serve industry and education. The standards simplify design, fabrication, analysis, and servicing of fluid power systems. The symbols describe component function rather than construction. In addition, they show how some of the fluid power components operate pneumatically, hydraulically, electrically, manually, and the like, in order to use the graphic symbol system to its maximum potential. The following rules must be understood and followed. 1. Symbols show connections, flow paths, and functions of components. They do not indicate conditions occurring during transition from one flow arrangement to another. Further, they do not indicate construction or values, such as pressure, flow rate, and other component settings. 2. Symbols do not indicate location of ports, shifting of spools or position of control elements on an actual component. 3. The position or size of a symbol can be altered for component emphasis in a circuit without changing its meaning. 4. Each symbol is drawn to show normal or neutral condition of a component unless multiple circuit diagrams are furnished showing various phases of circuit operation. 5. Arrows used within a symbol envelope show direction of flow in a component as used in the application represented. Double-end arrows indicate reverse flow. The graphic symbols utilize elementary geometrical forms to depict components and circuits. These forms include circles, squares, rectangles, triangles, arcs, arrows, lines, dots, and crosses. Elemental symbols. The first elemental symbols are energy triangles. Figure 31. Dot. A triangle is used to represent a conversion point of energy and its direction of flow. A shaded or darkened triangle as seen to the left indicates the energy medium is a fluid, such as hydraulic oil. The clear triangle on the right denotes the energy medium is gaseous. Orientation of the triangle will indicate the direction of energy flow into or out of the component. A dark triangle pointing out of a component envelope would indicate the component is generating energy, such as a pump, and that the medium is a fluid. Another example might be a clear triangle pointing into the component, meaning the energy medium is pneumatic and the component is absorbing or using this energy to do work, such as a pneumatic motor. Dot. We will see examples of these later. Rotating shafts are shown by a short solid line connected to the component outline. An arrow is used to indicate the direction of rotation. The arrow is always assumed to be on the near side of the shaft, and may denote either uni or bidirectional rotation. Basic components. The basic component symbols used are the outlines of circles, squares, diamonds, rectangles, and a few other geometrical features. Figure 32. Dot. These raw component symbols or envelopes will have supplemental component symbols or elements added to them in order to create or illustrate a specific type of component such as a valve, pump, or motor. Size of the component's outline may be varied to emphasize certain components or indicate a difference between a main and auxiliary component. Otherwise, variations in size are not an indication of the component's physical sizes. Tubes, hoses, and internal passages. 3 types of lines are used in graphic symbol illustrations to represent tubes, hoses, and internal fluid passages that connect the hydraulic components. 1 working line. A solid line is used to show a hydraulic working line. The working line carries the major flow of oil in a hydraulic system. 2 pilot line. A dashed line is used to show a hydraulic pilot line. The pilot line carries a small volume of oil used as an auxiliary flow to actuate or control a hydraulic component. The length of the dash will be drawn at least 10 times its width. 3 drain line. A dashed line is used to show a drain line that carries leakage oil back to the reservoir. The drain line will be illustrated as a dashed line with a length of the dash less than 5 times its width. Some other symbols are 1 enclosure line. The enclosure line is used to illustrate the boundary of the area of a machine in which hydraulic components are contained, e.g., an operation compartment or the front half of an articulated machine. 2 instrument line. The instrument line is used to connect an instrument to its sensor. Crossing lines. Here are 2 techniques used for representing both lines crossing and joining. Figure 33. Dot. It is important to note that graphic symbols may be drawn several different ways to represent the same thing. First, let's take a look at the techniques where A and B are used to represent lines crossing. In method A small half-circular line is used to jump or cross another line. The alternative method B merely shows the lines crossing each other. On the right, 2 methods are used for joining lines. The standard and most desirable way to show lines which join is to use a solid dot at the point of junction as seen in C. Quote, an alternative method is seen at D, in which the lines join without their connecting dots. This may appear confusing at first. since this is also a way in which lines crossing may be shown as in B. The way to determine the type of junction you have will depend on which of the other techniques is used throughout the rest of the circuit to represent line crossing or junctions. The key to determining the type of line junction seen in figure 34 at point 1 in views B or C will be dependent on the other technique used throughout the circuit. If a small half-circular line is used to depict lines crossing, then lines joining may be drawn with or without a connecting dot as seen in views A or B. Both methods are correct. Whichever method is chosen, it must be used consistently throughout the entire circuit. In a similar fashion, when a connecting dot is used to indicate lines joining throughout the circuit, then lines crossing can be shown with a half-circular line as in A or without it as shown in C. The important point to remember is that the technique chosen will be used consistently throughout the circuit. View D shows what would happen if the same method was used to illustrate both line crossings and junctions in a circuit. This is incorrect because no one would be able to differentiate between the two. Hydraulic lines. Hydraulic lines are used to connect the various components together to allow transmission of fluid in the circuit. The lines can be either tubes or hoses. A tube, figure 35, is a rigid hydraulic line usually made of steel. Tubes are used to connect components that do not move in relation to each other. Tubes also generally require less space than hoses and can be firmly attached to the machine, resulting in better protection to the lines and a better overall machine appearance. Hydraulic hoses, figure 36, are used whenever flexibility is needed, such as when components move in relation to each other. Hoses absorb vibration and resist pressure variations. Hydraulic tank. When construction machines and equipment are in the design stage, considerable thought is given to the type, size, and location of the hydraulic oil tank. Figure 37. Once the machine or equipment is in operation, the hydraulic tank functions as a storage place for the hydraulic oil, a device to remove heat from the oil, a separator to remove air from the oil and allows particles to settle out of the oil. The hydraulic oil tank main function is to store oil and ensure there is enough oil for any requirements of the system. Tanks must have sufficient strength, adequate capacity, and keep dirt out. Hydraulic tanks are usually but not always sealed. Tanks are mounted in any convenient location, sometimes as part of a major component housing. The components of the tank are fill cap, side glass, supply and return line, drain. Fill cap. The fill cap keeps contaminants out of the opening that's used to fill and add oil to the tank and seals pressurized tanks, figure 38. Sight glass. The sight glass, figure 39, is used to check the oil level according to the operation and maintenance manual. The oil level is usually correct when the oil is in the middle of the sight glass. The oil level should be checked when the oil is cold. Refer to manufacturer's specifications for the correct procedures for reading oil level. Breather. The breather, figure 40, is fitted to unpressurized tanks and allows atmospheric pressure to flow in and out of the tank. Drain. Located at the lowest point in the tank, the drain is used to remove old oil from the tank. The drain also allows for the removal of water and sediment from the oil. Drain plugs often contain a strong magnet to capture particles at the bottom of the tank. Supply and return lines. The supply line allows oil to flow from the tank to the system. The return line allows oil to flow from the system to the tank. Pressurized tank. The pressurized tank is completely sealed. Atmospheric pressure does not affect the pressure in the tank. When the oil circulates through the system, it absorbs heat and expands. The expanding heated oil compresses the air in the tank and creates a positive pressure in the system. Pressurized tanks prevent the entry of dirt and moisture and help force oil into the hydraulic pump. Air pressurized reservoirs receive air from the vehicle's compressed air system, although these are not used often. Never open the reservoir when it is pressurized. Thermally pressurized tanks rely on the expansion of the oil as it is heated to exert a slight pressure on the surface of the oil. The pressure relief valve controls the pressure in the tank and the vacuum valve prevents negative pressures when the system cools. Vacuum relief valve. The vacuum relief valve serves two purposes. It prevents a vacuum and limits the maximum pressure in the tank. The vacuum relief valve prevents a vacuum by opening and allowing air to enter the tank when the tank pressure drops to 3.45 kilopascals, 0.5 psi. When pressure in the tank reaches the vacuum relief valve pressure setting, the valve opens and vents compressed air to the atmosphere. The vacuum relief valve pressure setting may vary from 70 kilopascals, 10 psi, to 207 kilopascals, 30 psi. Filler screen prevents large contaminants from entering the tank. Filler tube allows the tank to be filled to the correct level but not overfilled. Baffles prevents the return oil from flowing directly to the tank outlet, allowing time for bubbles to rise to the top. It prevents the oil from sloshing, which helps reduce foaming of the oil. Ecology drain, used to prevent accidental spills when removing water and sediment from the tank. Return line, returns oil from the hydraulic circuit S to the tank. Return screen, prevents larger particles from entering the tank but does not provide fine filtering. Pump pickup line. The pump pickup line directs oil to the inlet side of the pump. The line does not normally touch the bottom of the tank. This prevents sediment at the bottom of the tank being directed to the pump. Vented tank. The vented tank is the most common type of tank. It has a breather that allows air to enter and exit freely. Therefore, pressure inside the tank is atmospheric. An air cleaning element or screen is usually fitted in the vent to reduce the entry of airborne dust. Graphic symbol hydraulic tank. The vented reservoir symbols, figure 43, are shown to the left under nearly an open-topped box or rectangle. A pressurized reservoir is drawn as a completely closed box. Return line connections can be either above or below the fluid level. Examples of both types are shown. The reservoir symbol is one symbol which can be drawn as many times as necessary on a circuit. Schematic to reduce the number of lines which must be drawn. Although the symbol may be drawn several times, it only represents one tank unless otherwise specified. Fluid filters. The general symbol used for a fluid filter is an empty diamond as seen in figure 44 above. Several different types of fluid conditioner symbols can be made by making slight changes or additions to this basic symbol. First is a filter or strainer, shown in figure 45 above with a dashed vertical line inside the basic symbol. This represents the filtering media which the fluid must flow through. A line drawn horizontally across the bottom portion of the symbol, as shown in figure 46, represents the separated matter that has settled to the bottom, such as water. A short line extending from the bottom of the symbol, shown in figure 47, represents a manual drain. If the short line is not on the symbol, it must be assumed to be a manual drain. Nothing on the symbol will indicate. Automatic drains will be represented by a small V placed below the horizontal separation line as shown in figure 48.